Great. A lot of the width of that error bar comes from the fact that there's a lot of chemistry relevant in this situation. The second reason is that aerosols affect human health. This is just a figure from the 2019 Global Burden of Disease study showing number of deaths worldwide by risk factor, and air pollution, which is dominantly aerosol particles, comes in here at number 3, causing just shy of 7 million premature deaths per year. And of course, you all know what aerosol pollution looks like. This is just a picture from Minneapolis a couple summers ago, and we had a lot of air quality events with its impact on health and visibility and all of that. So getting into the chemistry, this is a figure showing the chemical composition of aerosols kind of across the northern hemisphere. And what I want to point out here is that chemically speaking, that aerosol burden is about half organic and half inorganic. So the organic component is in the green and the inorganic is in all of the other colors. And so the one thing to highlight here is that the inorganic part, we can characterize most of that mass with the 4 species shown there, right? Sulfate, nitrate, and ammonium and fluoride. Whereas the organic part that's shown here as a homogeneous green is actually composed of probably tens of thousands of different molecules. And so it becomes a lot harder to describe that component. And so here we're showing that organic aerosol is an important component of the global aerosol burden. And most of that is secondary, right? So it's things emitted into the gas phase that get chemically transformed into things that are condensable into aerosol particles. And so that chemistry that transforms something from the gas phase to the particle phase is what we'll look at here. So most organics or VOCs are emitted to the atmosphere as hydrocarbons. So we'll show that here as RH. And then those can be oxidized by a variety of oxidants, most commonly OH, to form what's kind of the key intermediate in this chemical pathway, RO2 or organic peroxy radicals. And that's a key intermediate because at that point we get this big set of branching to a whole bunch of different reaction pathways. And it's that product distribution that controls the properties of what comes out of this oxidation, and hence how much is low enough volatility to contribute to the production of SOA. So that's kind of the underlying chemistry. And then if we turn to models that try to describe SOA broadly, those are largely based on lab experiments, right? So you do a lab experiment, you develop some kind of parameterization, and you put that into models. But our current kind of state of the science models really can only explain less than half of the observed variability in organic aerosol. So this is a figure showing two different schemes of varying complexity for SOA in the GeoSchem chemical transport model, and comparing them against observations, and you see an R squared of about 0.4, right? So we're only capturing about 40% of the observed variability. And this is kind of the key piece of what a lot of the work we're trying to do in terms of addressing this gap between models and observations. And so kind of the rest of what I'll tell you today is some starts at an attempt to see if we can get this number to be better. But in order to kind of tell you about what we've been working on, I want to kind of tell you how we've gotten here. And so here comes the kind of historical interlude that I alluded to. So we're actually going to zoom back all the way to 1870, which is the year of the very first recorded lab experiments of SOA production. And they were done by John Tyndall, who y'all may know of as he's kind of most famous for having been the first person to discover the greenhouse effect. But he did a whole bunch of really interesting things, including studying SOA production in the experimental setup shown here. So he had this glass tube in the middle that he would fill with some organic vapors from the right side there. And then he had this lamp that he would shine on it. And when he irradiated the tube with light, he observed the formation of a blue cloud. And he describes it in really fun terms. He says, here and there also amid the white and coarser sections of a cloud, spaces of a delicate blue would reveal themselves, reminding one of the color of a pure sky. The words wonderful, beautiful, lustrous, and others of a similar nature occur frequently and naturally in my notes of this period. For in those earlier experiments, the cloud forms obtained were so amazing and their colors and textures so fine as to rivet attention upon them alone. Anyway, he goes on, and it's really quite a fun paper if you want to read it. But the point here is that he observed the formation of a blue cloud, and based on what he understood at the time about wavelengths and scattering, he deduced that he had formed a bunch of submicron particles, which are, of course, what we would now call SOA. Okay, so we can zoom forward nearly a century to the 1950s, and that's when you get the work of A.J. Haagen-Schmidt, who was trying to figure out the chemistry behind urban smog in LA. And so he put a combination of ozone, some typical urban VOCs like olefins, and NOx in a chamber, exposed that whole chamber to sunlight, and then watched the chemistry unfold, which of course included the formation of particles. And so what we get from his work is really this understanding that particles can form from sunlight-driven photochemistry of urban air components. A few years later, we have Wendt, who postulated that same chemistry that Haagen-Schmidt was observing in those urban environments could also play a role with biogenic VOCs and be kind of the cause of the blue haze that was often observed over forested regions. And then by the time we get to the 1980s, we start to get this kind of proliferation of studies of SOA that we're looking at a whole wide variety of VOCs, all of which kind of provide this further evidence that SOA is really a product of photochemistry from both anthropogenic and biogenic VOCs. When we get to the 1990s, we start to get a lot more sophisticated analytical capabilities, which let us be more quantitative in our measurements, right? So now we can measure actual SOA yields instead of just saying, yes, we form SOA. And so the first thing that came out of these was people started to notice that the yield that you get depended on the amount of NOx you had in your chamber, right? So that was kind of the first demonstration that the chemical environment in the chamber really mattered. And so as a result, people started to characterize their experiments based on the ratio of hydrocarbon to NOx concentration. But I do want to point out that at the time, this dependence on the hydrocarbon to NOx ratio was thought to only be a result of changing ratios of oxidants, right? So the effect of NOx on the nonlinearity of OH or ozone or nitrate, and that was kind of the only effect that people thought was going on in here. And so those studies really informed kind of our first regional and global models of SOA. Right, we used the yields that were measured in those experiments, and we included the NOx influence on those oxidant ratios, but the SOA yields for a given oxidant didn't have any specific NOx dependence. By the time we get then to the early 2000s, we start to get some evidence that the effects of NOx are perhaps a little bit more complicated than that. And so one example is that we see that the relative abundance of hydroperoxides, which come from the RO2 plus HO2 reaction channel, that has a correlation with SOA yields. And we also get some studies that demonstrate pretty clearly that changes in SOA yields with NOx are not attributable solely to those changes in oxidant ratios. And so with those new pieces of evidence, we kind of came to this new understanding that RO2 chemistry was really important in controlling the amount of SOA you got, and specifically this competition between RO2 plus NO and RO2 plus HO2. And so as a result, we started to run kind of chamber experiments under limiting conditions, right? So you would make under conditions where all your RO2 would react with NO, and then where all your RO2 would react with HO2. And so the idea was that if you measured your yields at each of the two extremes, and then you could parameterize whatever was happening under intermediate conditions as kind of a linear combination of the what's happening at either end. And so you can imagine that if you had some kind of chemical coordinate that tracked that branching ratio, you could kind of interpret that as a mixing parameter to do that linear combination sort of estimate. And so yet again, these kind of experimental advances prompt updates to our model parameterizations. using those kind of limiting condition experiments. And in this case, we land on beta as this kind of chemical, relevant chemical coordinate. And so that's just the fraction of RO2 reactions that occur with NO. And so this was kind of back in 2010-ish. And this is largely still the same kind of framework for SOA parameterizations in models today. But I'll point out that, right, it has this issue where it alone cannot explain all of the observed variability that we've seen. So one of the reasons for that is that we've learned quite a bit about more about RO2 chemistry over the last 15 years or so. And one of the key advances is understanding that RO2 can undergo some unimolecular chemistry in addition to the bimolecular chemistry of the reaction with NO and HO2. And so these kind of RO2 isomerization reactions where the RO2 effectively oxidizes itself can lead to the formation of some really highly oxygenated molecules, which can serve as a source of SOA because they are lower in volatility. And so the importance of these kind of unimolecular reactions mean that we effectively need an additional chemical coordinate, right? Our beta parameter that tracked the relative amount of the two bimolecular reactions is fine for the bimolecular piece, but then we need effectively the lifetime of RO2 to bimolecular reaction shown here to tell us about the competition between bimolecular and unimolecular reactions. And so the other component of this understanding means that those kind of former SOA studies that really focused only on the two extremes of the distribution can end up missing out on key parts of the product distribution, right? One, they're not necessarily capturing these isomerization products, because if you're trying to force all of your RO2 to react, say, with NO, you're going to put a lot of NO in the system, right, and effectively shorten your bimolecular lifetime. So you miss out on those. And the other piece of this is that if you're observing SOA formation over multiple generations of chemistry, and you're targeting just one of these pathways, you're only going to end up with effectively one of those kind of 9 possible pathways on the right side there. And so you're not necessarily capturing different fates across different generations of oxidation. So we wanted to figure out if there was a way we could do some lab experiments in a way that kind of addressed these two problems. But in order to do that, of course, first we needed to figure out kind of what the atmospheric distribution of these chemical parameters were, right? So we have, again, beta is on the y-axis. That's our competition between the two bimolecular reactions. So as that increases towards 1, that's your kind of more polluted situation where you're dominated by RO2 plus NO. And then on the x-axis here is your bimolecular lifetime. So as you go to the right on that, the bimolecular lifetime that's longer, you allow more time for your unimolecular isomerization reactions. And so just to make that a little clearer, if you had some kind of unimolecular isomerization process with a tau uni shown with that dashed line, if your bimolecular lifetime was somewhere to the right of that, then you'd be dominated by isomerization. And if your bimolecular lifetime was shorter than that, you'd be dominated by bimolecular reaction. So we turn to the GS Chem chemical transport model to think about what these distributions are in the atmosphere. And so this is the distribution of tau. It's relatively narrow and centered kind of around about 100 seconds. And then this is the distribution of beta, which really spans that whole range from 0 to 1. And then we can look at where these two distributions overlap, and you get this nice little purple swoosh here. And the idea here, right, is that if we want to target the atmospheric chemical environment in terms of capturing atmospheric RO2 chemistry, we want to land basically as close to that purple swoosh as possible in our chamber experiments. And so we took a look then at kind of where all the past chamber experiments have landed. There's a variety of different approaches people have taken, but this kind of summarizes where the kind of 6 most common approaches to chamber experiments end up. And you can see we do actually span a pretty wide area in this beta and tau space, but we never actually land in the distribution that that we were after. And if anyone's interested, we can talk through more details of exactly what these approaches are and why they land where they are, but I won't bore you with all those details right now. So anyway, all of those experiments are largely chamber experiments, and they work in mostly the same way. So this will be kind of a summary of broadly how they all work. The picture is effectively a temperature controlled enclosure that's aligned with UV lights that simulate the sun. And then inside that, we have a Teflon bag where you can inject various analytes you're interested in, and then also sample out from other ports. This is a picture of the one I worked with as a postdoc, and we are a few months away from getting ours built here at University of Minnesota, and it will look relatively similar. So the first thing you have to include is an oxidant precursor, right? Something that when photolyzed will start to initiate the oxidation. So typically that's some combination of HONO and H2O2, right, which both photolyze to give you OH. Then you have to add your VOC, whatever you want to oxidize in order to make some SOA. And then we typically add seed particles, usually ammonium sulfate, and that's just to give everything some surface area to condense onto, right? Otherwise, the bag itself has a lot of surface area and everything would condense onto the walls where we couldn't measure it very well. And then you need some source of UV light to initiate the oxidation, and then you can kind of measure your products with a variety of your choice of analytical instrumentation, depending what you want to look at. So this is kind of broadly how they work. And the overarching reason for why we haven't yet achieved kind of that atmospheric RO2 fate distribution is because of some kind of fundamental laboratory constraints that I kind of started to allude to. First is that all of those analytical instruments, they need to have enough signal to surpass their limit of detection. And we also have to have our oxidation processes fast enough that we're out competing loss of things to the walls and loss of things to dilution, right? Because we have a flow of clean air that comes in to replenish whatever we've taken out to our instruments. And if you need enough product, especially if you're measuring something that has a relatively small SOA yield, it means you need to start out with a lot of carbon in your precursor. And then to oxidize that quickly, of course, you need a lot of oxidant. And so the kind of result of those fundamental constraints, if you will, are that it becomes really easy to push beta towards one of the extremes. And it also means that you end up shortening your bimolecular lifetime, right? Because when you add so much oxidant, you end up producing a lot of bimolecular reaction partners. And so, yeah, we have this kind of fundamental constraint of needing high quantities of carbon and high quantities of oxidant, and that makes it really hard to control this RO2 chemistry. So we wanted to figure out if it was actually possible to land ourselves in that atmospheric chemical space in these experiments. And so we did some modeling where we essentially logarithmically spanned every possible combination of initial conditions you could have it in your chamber, right? Spanning different concentrations of oxidant precursor, additional NO, your VOC concentration. And we did this, it's just some simple box modeling in foam, the framework for zero-D atmospheric modeling with MCM chemistry. And what you get is this, right? So underneath this figure is that same purple swoosh that I showed you on a previous slide that we get from GS Chem. And then overlaid on top of that are these green dots and lines. So the green or teal dots, those are ones in which the chemistry is fast enough that we can achieve 2 generations of oxidation in an 8-hour experiment, which is what we chose as kind of our criteria for, is the chemistry fast enough to be able to measure things before we lose it all. And then the green lines are ones where the chemistry is too slow and we cannot achieve both of those generations of oxidation in that experiment. And so you can see our fundamental constraints do mean we can't access a portion of that purple swoosh in our experiments. But I want to point out one bit of nuance in this figure, which is the orange and pink lines that I'm showing there. And so In this study, we were focused on isoprene, and so those two orange and pink lines correspond to the two first generation isoprene RO2 isomers that can undergo isomerization. So those are the two relevant kind of tau unis for this chemical system. And so effectively, if we want to achieve an atmospheric balance of bimolecular and unimolecular chemistry, all we need to do is be about an order of magnitude to the right of either of those two lines. And so we can actually achieve that in all but the very lowest beta conditions. And so that's what we attempted to do here. And I mentioned that we decided to kind of test this framework with isoprene as a model compound, which of course comes from deciduous trees and is really important in terms of the global biogenic VOC budget. So the experiments I'll show you were ones we ran at MIT in the MIT chamber. So the chamber is a 7.5 cubic meter chamber, has 340 nanometer UV lights that surround it. And we initiate each experiment with 100 ppb of isoprene. We include a small amount of acetonitrile, which is chemically inert on the timescales of these experiments. So that lets us have a tracer for dilution. And then we add HONO and H2O2 in different combinations as our oxidant precursors in combinations informed by the modeling that I showed you on the previous slide. And then we had some ammonium sulfate seed, again, to serve as a surface area for condensation. And so connected to the chamber, then we had an aerosol mass spectrometer for looking at aerosol chemical composition, scanning mobility particle sizer for looking at size distribution of particles, proton transfer reaction mass spec for looking at the relatively unoxygenated species, an ammonium chemical ionization mass spec for looking at the more oxygenated species, and then some ozone and NOx monitors. And so I won't show you information from quite all of these today, but we'll look at some different bits and pieces of these. But the idea here is that we were really trying with this whole suite of instruments to capture as much of the chemistry in both the gas and the particle phase as possible. So we'll start by looking at the gas phase products measured by the ammonium sieves. And what we did with these measurements was use them as kind of a check on did we actually achieve the chemical conditions we were after that the modeling told us that we would be. And I'm going to give a quick shout out to the two graduate students I worked with on these experiments, Nadia and Matthew. And so in each of the experiments, we measured a time series of the product distribution. And so I'm highlighting here 3 products that we've picked out as kind of marker species for each of those 3 RO2 pathways. And so you can see in this case, we have a high beta experiment, right? And so our product distribution is dominated by the green trace here, which is the nitrates that comes from RO2 plus NO. And so to facilitate comparison kind of across all of the experiments, we took the time series from each and plotted the signal as a function of delta isoprene to get a yield right from the slope of that. And then we turned the yield from those slopes into a pie chart. So you'll see a pie chart like this for each of the experiments. And again, this is that high beta one that's dominated by the green, the nitrate. So we can kind of put these pie charts on this distribution to see if we did indeed achieve what we were after. So again, this was the one we looked at on the previous slide, dominated by the nitrate. And then down here at a beta of more or less 0, we get a product distribution dominated by the hydroperoxide in yellow, which is what we were hoping for. And then our most exciting experiments were these ones where we really started to get quite close to the target purple swoosh area, where we do indeed get competition between kind of all 3 of these RO2 fates. And so we did a whole bunch of these experiments shown here, where we really tried to approach as close as we could to that atmospheric RO2 chemistry. And you can see the trend follows exactly what you would expect, right? As you go up, you have more and more green. As you go down, you have more and more yellow. And as you go to the right, you have more and more blue, right? So this was our kind of confirmation that our experiments did indeed achieve the conditions we were after, including these conditions where you have competition between all 3 of these RO2 fates. So then we can turn to the SOA that we produced from each of these. And so this is just the SOA yield, right? So the total amount normalized to the amount of isoprene consumed as a function of beta. And what I want to point out here is that this is a nonlinear trend, right? And so it tells us that assumption that's in our models that you could take, the yields that you measure at the two extremes, and you do a linear combination of those to get something in the middle. It is not doesn't quite align with this these data that we've collected. So that's the SOA amount, and then what we've been working on more recently is thinking about what this means for SOA composition and how well we're capturing atmospheric SOA composition in these measurements. And so this is what a student in my group, Nora, has been working on over the last couple of months, is saying, okay, we've run these experiments. We think those intermediate beta conditions better tell us what's in the atmosphere, but can we compare the product distribution that we measure to actual ambient observations and see if we get something that makes sense and looks more like what we've measured in the ambient. And so to do this, we are comparing our isoprene chamber experiment spectra against the ambient AMS spectra measured during the SOAS campaign. So that was a field campaign in 2013 in Centerville, Alabama. So that's the Southeast US, a highly isoprene dominated environment in terms of VOC reactivity. And so we're comparing the AMS spectra between these together. We apply a weighting factor to both spectra. We weight both by the mass to charge ratio and by the peak intensity. And the idea here is just to increase the significance of those lower abundance high M over Z ions, which are the things that are actually distinguishable between the two spectra. But we apply the same weighting to both spectra. And so that gives us spectra that looks something like this. And then we can simply compare those two spectra. We'll do that here with a scatter plot. So we have the ambient fractional abundance from our spectra on the y-axis, and then our experiment on the x. And so this is comparing our two extreme experiments, right? So these are those really high NOx, really low NOx, the things that basically mimic what people have done before, and the things that inform our model parameterizations. And so again, this is ambient on the y-axis, and then low NOx experiment on the x on the left, and high NOx on the right. And you can see the agreement between these is not great, right? They're kind of we don't get super close matching. But what's super cool is if these are the same two plots that you saw before, and now we can slot in our intermediate beta experiment, which we hypothesized would better match what is observed in the ambient. And indeed, we get an R squared of 0.77. So we're explaining almost 75% of the variability that we're observing in this intermediate beta experiment, which was very satisfying to see. And I will highlight here that you don't get that same result again with a linear combination of the two extremes to that beta of 0.2, which is what I'm showing on the left here, right? So you really do need those conditions where you're perhaps getting two different fates at your two generations, and you have the role of RO2 isomerization and whatnot. So that was just comparing kind of 3 of our experiments. We did a whole bunch of those. And so here, to kind of facilitate comparison across all of them, we are showing the cosine similarity score between the experimental and ambient spectra as a function of beta. And so cosine similarity score, effectively, the higher it is, the closer it is to 1, the more similar your spectra are. And so you can see, again, that we are maximizing that similarity in those intermediate beta conditions there. So this has left us with a few kind of open questions. The first of which is that I think I forgot to say this, but all of the experiments that I showed you that we did here were dry experiments. And the Southeast US is a really humid place, especially in the summer. And our kind of working understanding of isoprene SOA says that actually a lot of the SOA mass comes from aqueous reactive uptake of IEPOX, which is OH oxidation of the R2 plus HO2 product. And so it was actually kind of unnervingly surprising to us that we had such good agreement between our ambient observations and our experiments, given that this chemistry shouldn't have been happening in our experiments. So that's kind of an outstanding question. The other piece of this is that though the Southeast US is an isoprene dominated environment in terms of reactivity, isoprene SOA yields are relatively small. And so most estimates say that about half of the SOA mass in the Southeast US should be isoprene and the other half should be monoterpenes. Even though monoterpenes are lower in concentration, their SOA yields are much larger. So that's also a puzzling piece of this, of why can we explain so much of the ambient variability if we're only looking at isoprene in dry environments. So when we get our chamber in due course, these are kind of some of the questions that we will start to go after with that. So I just want to kind of wrap up by talking about this in a little bit more of a kind of bigger picture context. So these kind of our three pillars of atmospheric chemistry, the three-legged stool or whatever you want to call it. But we kind of started by talking about how for many decades we've had lab experiments that are used as the parameterizations for SOA for models, right? And we thought about that back from 1870, but also much more recently. And then, of course, took this look of, okay, how do models compare against field observations? And we come up with this conundrum of, we can only explain 40% of the observed variability. And so then we decided to say, okay, can we use our models in a different way, not just for validation of field observations, but actually use them to figure out what conditions we need to be able to span in our laboratory experiments in order to capture what's happening in the atmosphere. So that's what we did, and we did this whole series of experiments shown here. And then we took those and we said, okay, let's go and compare them to field observations and see if are we actually doing better in the ways that we thought. And so, of course, then the next steps here, as I alluded to on the last slide, are now we have a bunch of things we can't quite explain in those. And so that brings us back in the lab. And hopefully at some point in a few years, when I give an updated version of this seminar, we'll be at the stage where we can do the updates to the model parameterizations and show that we can predict what we see in ambient field measurements better, but that's down the line a little ways. Anyway, before I finish, I just want to give a bunch of acknowledgements to my group here at Minnesota, and the stuff I showed at the end was done by Nora, who's on the right there. Also want to give a shout out to the two groups I worked with at MIT on the Pearl group with the experiments and the HEALD group with all the modeling that I showed, UMN Chemistry and NSF for funding, and then a variety of collaborators, including the Jimenez group at Boulder, who provided the SOAS AMS data, and then the Koich group at Harvard and Aerodyne, who contributed a bunch of the instrumentation that we used in all of those chamber observations. And I think I talked faster than I was aiming to, so there's loads of time for questions, and yeah, thanks for coming.
Thank you. Quick question, Hannah.
Yeah.
Chamber that you're building here at Group M, will you be able to control temperature, humidity, specific humidity for these experiments?
Yeah, so it'll be in a temperature controlled enclosure that lets us control from 12 to 45 C is the temperature range. And then, yeah, we can control humidity just by, instead of sending in dry air as our kind of dilution flow, just bubble in humid air and then control with a balance of 100% humidity and 0% humidity. So yeah, hopefully we'll be able to get at some of those, why do we see lots of isoprene SOA when there's no water?
Yeah, kind of related to that question, do you anticipate any like major wall losses with the more humid chambers?
Yeah, that is one of the tricky things is that humidity does tend to change your wall loss properties. I'm hopeful we can do some kind of control experiments, right? If you put in some well, I guess if your question is vapor wall loss versus particle wall loss, for vapor wall loss, we could put in a bunch of VOCs and not do any chemistry and compare how fast they decay in wet or dry conditions. For the particle wall loss, we have a relatively good idea of how much that is, just because since we use seed particles made of ammonium sulfate, we can watch the decay in sulfate and just normalize to that. So that's relatively simpler, but yeah, it's a conundrum of any chamber experiment ever.
I have a question. So for this R squared, it's interesting because it's sort of in your history, if you go back to kind of the evolution of this field,
Yeah,
there was kind of a big push on SOA when we realized the models couldn't explain the abundance. And now maybe we're doing better with the abundance, but we're not getting the sort of, maybe for the wrong reasons, because they don't correlate.
yeah.
And I'm wondering what's your sort of sense, if you had all this right in the model, all this sort of source stuff you talked about, right? What would those R squared values be? Like, to what degree do we have the sinks right, for example?
Yeah, no, it's a good question. And yeah, so we largely get the like average magnitude, right, which considering that like in this case, both the simple and the complex scheme get it right, and they work somewhat differently, I think means that we're probably getting it right for at least partly the wrong reasons. But in terms of giving, I don't have a quantitative answer to give to you. But I like to think the answer is all chemistry, because I think the chemistry is more fun. But a big part of the answer is probably deposition lifetimes too, and I am not the person to give you the right answer on that, but we will plug away at this as hard as we can on the chemistry, and then what's remaining is probably depositional or loss or something. But I think just given the non-linearities that I showed today, I think we can start to get it. We should be able to improve this with some improvements to the chemistry.
I mean, the small difference between those two bars is a little disconcerting, right?
Yeah.
Well, from such a simple chemistry treatment to a more complex treatment, and you did that little.
Yeah, it's disturbing for sure.
Yeah, I have a question. So I think are the comparisons you showed, I think for the ammonium sims, is that correct? You're comparing the spectra between the ambient measurement.
AMS.
Oh, okay.
The ammonium sims was all the
Okay, so
pie charts.
Yeah. Well, then I still think it.
That's okay.
Yeah.
Do you think that is the sort of chamber limitations that you sort of exploring in your science advances paper, is that partly an argument for synthesis in terms of being able, like, it's sort of, you have this limit on the amount of time you can look in these chambers, so how much does it help to just start
Oh,
chemistry
with an
with
intermediate.
an intermediate?
Yeah. That's a good idea. I think the one challenge of that is a lot of people run their isoprene oxidation experiments starting with isopoo, and then you make IUPOX, and I think that's a lot of how we've ended up with in understanding that. I mean, you get a lot of SOA from that, right? But you also get a lot of SOA when you don't do that chemistry. And so my worry in that regard would be that we would pigeonhole ourselves down different chemical pathways. But it totally could work. I think we've been thinking about it a little bit more from the other end of, can we improve the LODs on our instruments, which would effectively do the same thing? So we've been talking to Chris Hogan, about building an aerosol concentrator to put in front of our ACSM. The problem is then you need a big amount of flow from your chamber, but, anyway, that's one idea we had to get at that, but the starting with an intermediate is, well, the other nice thing about that is you could start with like something photolabile that makes directly an RO2, right? And then you don't have to worry about what your RO2 distribution is. But yeah, it's fun to think about. Brent, did you have a question?
A couple of quick comments and then one question.
Yeah,
Well, while you're waiting for your lab, if you want a flow tube chamber to work with, there's one right across the hall here in storage. There's a PAM chamber.
oh, cool.
If you have any interest in trying that out.
Good to know.
Temporary.
Yeah, thank you.
The other thing is the weighting of the mass spectra weighting.
Yeah,
So Yun Chiang, who made that, she was very concerned that people weren't discovering that, and I'm gonna report to her that it thought in the presentation.
great.
I'll let her know about that. And field observations was my last thing, so. You know, coming here to Minnesota and we'll have almost a year experience here. What are some interesting thoughts you've had about potential field campaigns, collaborative, things that we could do, but are there like, specific questions that you'd be interested in around perhaps the Twin Cities specifically?
Yeah. Yeah, lots of different things. I think the one that would thematically relate to this most is, well, what I showed here is the global distribution of RO2, and it's a little bit different in urban context. Well, at least historically, it meant you would move farther towards the higher beta space. Right, but in theory, we're moving towards lower and lower NOx conditions, and so I think if we made a long enough time record of some of these oxidation products, we could effectively trace out movement in this purple swoosh over time, and I think that would be really cool. That's my long-term vision. We'll see if we get there, but I think we could totally do that here and effectively watch that change as our vehicle fleet electrifies and that kind of stuff, which I think would be really neat.
Is there a way to like tap into campaigns that happened over the pandemic, for example, that watch those transitions faster?
For sure. If you have ideas on some people to reach out to ask about that, I am all ears.
There's a couple, RO2 in the gas, sort of much smaller RO2 in the gas phase reactions with OH that are I'm starting to realize are actually relevant. Could that play a relevant role in this context?
Yeah, so I guess the one thing I skipped over entirely for the sake of not talking in a million circles is the role of RO2 chemistry and RO2 NO2 chemistry. So we get the RO2 HO2 ratio wrong in chambers mainly because H2O2 is a source of HO2, and so if you're using that as your oxidant precursor, you're adding a lot of HO2. The biggest problem I've thought about in terms of RO2 chemistry is the fact that the RO2 distribution in the chamber is way different because you almost exclusively have big RO2 instead of little RO2. And but to answer your question more specifically, we did do some calculations to say, okay, even if the RO2 OH rate is like as fast as it might be for some of those small ones, it's still relatively minor in terms of the total RO2 fate distribution, just because the concentrations of everything else are so high.
That'd be the case in the atmosphere too.
That is a good question, because then you have more of those little RO2s. I'm not sure. You have to think about that.
Questions on that? All right, thanks so much, Hannah.
Thank you.
I love how Congressman is smoking in his lab in that photo.
I know, right? It's so funny.
It's for the sea aerosol.